Good morning. We're going to do a couple of fitting things with Microsoft Excel for the kinetics experiment. So first of all, we need Excel and we need some data. I have some fake data I have had in the oven for a while. I'm going to move that over just a little bit. I've got X data and I've got Y data. We're going to do two things today for the basically the sucrose lab and for the other kinetics lab. We're going to do a fit with Microsoft Excel, just a straight linear fit of a graph, and get uncertainty values from that, and then we're going to do a weighted fit. So those correspond to the two different steps that we have. But at least for the first step, just to be a little bit less helpful, I guess, or to make you do a little bit more work, we're not going to use the same type of data that you will actually have in, say, the sucrose. So we're going to use a linear function, whereas the sucrose data is exponential, but the process will be the same. First thing we want to do is make sure Excel has what we need installed. So we're going to go up to the, I thought we were going to go to the Office window. We'll go to File, and then Options, and then we want add-ins. And we want to make sure that the Solver add-in and the Analysis tool pack are included. So if those are not up there, if they're down in the inactive Applications add-in, double check those and they will install. We should be able to go to Data and then see Data Analysis and Solver. So we want both of those. Now the first thing we're going to do is we're just going to fit this data using Excel's regular old linear fit routines. So first of all, I want to graph the data, and I'm going to add a trend line to it. So I'll just highlight my data, go to Insert, and I'll do a scatter plot, and there's my data. I want to add a trend line to this, so I'm going to go to Layout, Trend Line, and then I'm going to go down to More Trend Line Options. And here I can choose what kind of trend line I want. I want a linear one. I want to display the equation on the chart. We'll display the R squared value on the chart as well. That's fine. And we'll do OK. And there's my fit. We want to tweak a couple of things to this. We maybe want to change the number of sig figs that are up here in the trend line. So I'm going to right click on the trend line box and do Format Trend Line. Right click on that Format Trend Line label. And then switch to number, and then up the number of decimal places. We'll say 5 maybe. So now we have a much bigger number of significant digits to use. And this will be helpful if your actual trend line is tiny, if it's just minute, or if one of the parameters is very, very small. That will help. So we can actually get more useful information out of that. The next thing we want to do is to get an actual report from this. So I'm going to pause briefly, and we'll switch instructions and take that up. Okay, so now we're going to get we want to get some error estimates from this. So we'll go to Data, and then Data Analysis. And in here we have lots of options for data analysis. The one we want is regression, so we'll do OK. And now it pops up a regression wizard. So we need to add in the Y range and the X range. So we're going to, you can either manually input the Y range, or you can click on these guys and then highlight the range that you want, and then click on it again. Do the same for the X. There's the X. And then we can do a variety of things. We can fit, so we'll do a line fit plots. We can get confidence intervals at the 95%, and we're going to send it to a new worksheet apply. So it will give us a new worksheet with the results. If I click OK, now I have all of this stuff, and you can see it created sheet 4 down here. So I have a lot of information now And what I really care about are the coefficients and standard errors down here. So I'm going to just make these a little bit broader. So now my coefficient is 2.149, blah, blah, blah. That's my intercept. And then the slope is 1.02. And then I have the standard errors in those. So those correspond to one significant, or one standard deviation. So those are the errors that we'll want to use in our other fits. Sheet 1 still has my data. And just to remind you, if I go to regression, it will give me a variety of ways to do this. Next thing we might want to do is we want to do the Arrhenius type fit. So I'm going to first of all get rid of my trend line. So there's my y data. And when we do the Arrhenius fit, we are going to do a weighted fit, which means we have to do it almost manually. So what I'm going to do is actually tweak some of my y data just to make it bad. And then we have some error, right? That was the whole point. So we get error with these. I'm going to make most of these 0.1, except for the one that's very off, in which case I'll make that 2.5, we'll say. And I'm going to show you how to do two types of fitting. We're first going to do the fit without the error, and then we'll include the error. So if I'm going to do what's called a nonlinear least squares fitting routine, I need guesses first. So I need the parameters. So I'm going to have a slope. So I'll give myself a slope label, and then an intercept. And looking at the data, I'm going to guess the slope is 1, and I'm going to guess the intercept is, I don't know, 2. So just guessing at the parameters. If I look at the y data, the slope is approximately 1, the intercept is about 2. Then I'm going to include a column that is the modeled data, basically. So I'm going to use my slope and intercept guesses to create a actual fit, more or less, or a model of the data. So in my case, F2 here, I'm going to include the formula for a line based on the slope and intercept values that I have and the data in the X data. Now, I only have a single value for slope and a single value for intercept, which means I'm going to have to anchor the formula to those cells. So formula, first of all, that's going to be an equals, and then I want the slope. So the slope is in A2, so I'll do A, and then to make Excel always go to cell number 2, I'll use a $sign, and that's basically the anchor in Excel. So a $2 times, and now I want the X data, so that's C2. I can just click in there. And then the intercept, which is B2. So plus B, and then I want to anchor it again, so $2. So there's my modeled Y value. And I want to do that for the rest of the data. You can copy and paste. You can also just grab the lower right and drag, and it will autofill the formula. And you can see as we go down that it's always A2 and B2, but the C value is changing, which is exactly what we want. The next thing I want to do is come up with a difference, and in fact the square of the difference of the model and my Y data. So this is going to be square difference. Again, it's a formula, so I'll do equals and then parentheses. So I'm going to do F minus my Y data, close parentheses, squared, so raised to the 2. This one I don't have to anchor anything because I have the column for F, I have the column for D, so I'm just going to drag it down, and there's my square difference. The last thing I'm going to do for a nonlinear least squares fitting is to sum up all of the squares. So down below all of the squares, so that's G17, I'm going to type equals and then sum, open parentheses, and then all of the data in G, so G2 to G16, close parentheses, enter, and I'll give that a name as well. So that is the sum. So right now I have a sum of 22.8, and the way nonlinear least squares fitting works is I'm going to try to minimize that value. I'm going to minimize the difference, actually the square of the difference between my model and my actual data. So to do that, I go up to Data, and then the Solver dialog, and then I'm going to set the objective to be the sum, so G17, and then I want to minimize it. The only other thing I need to worry about is, so we're not doing any constraints. We have GRG nonlinear, that's fine. We'll go into options, and we are going to click on the GRG nonlinear, double checking all of these methods, iterations, ignore, yep, okay. We want to make sure use automatic scaling is there, because that will change the step size basically, or the tolerance based on the values of your parameters in A and B. That's what we want. So now I do OK and click solve, and by changing variable cells, yeah, forgot that. So I just highlight my two variable cells, A2 and B2. I click solve, and now it's done. I'm going to check keep solver solution, and now my sum went down to 17. It's a little bit hard to tell what has happened because I don't have a fit yet. I have the slope and the intercept, those changed. I can add the fitted data to this. So I'm going to go right click on the graph, select data, and I'm going to add an entry. So this will be our model or fit. The x values are the same, so I'll just highlight my x values. My y values now are the model, so I'll click those. Okay, and there we go. So if we look at this, you can see that just looking at the red versus the blue, there's a little bit of a bias in the data caused by this one blue point up here. That one blue point, though, has a really pretty big error compared to the others. All the others are 0.1, that one is 2.5. So to do a weighted fit, what we're going to do is we're going to tell Excel to give more weight to those data points that have small error. And the way we can do that is by dividing the difference by the error value. So bigger error, less weight. So let's do that. So let's go into our formula for square difference. I'm going to add a set of parentheses before the squared, and then I'm going to divide by the error, which is in E2. So now that makes it bigger, but that's fine. I'm going to update all of those cells. My sum gets much bigger, 224. I'm going to copy the slope and intercept here just to give you an idea of what those are, or what those will be. I'm going to go back into Solver. Everything is the same. I'm still setting the objective, the minimization of the sum by changing A2 and B2. Going to check solve, keep solver solution, and now you can see the slope is different. It's higher, the intercept is different, and if you look at the graph matches more of the other data, so that one data point that has the big error is no longer dragging the entire fit line up. So this gives us a more accurate set of parameters for the slope and the intercept. And those are the values that we want to report when we do the Arrhenius plots and the concentration plot in the fluorescence experiment. All right. This all can also be done on SigmaPlot if you have access to SigmaPlot. Not everyone does. There are computers in the lab that have it, and there are instructions on Blackboard if you would like to do it that way. Either way will work, but we do want to do a weighted fit. That's the important part for this. Good luck.